All right. So we already completed this slide deck in the last class, uh, but I felt like I kind of rushed through the sum and carry section, and you may or may not have gotten it properly. So I will spend 5 minutes of today's class to quickly review this. All right. So if you have already got it, that's great. But otherwise, I would request that you pay attention. So this was the truth table for an adder. Okay. And what I try to convey here is that an adder has three inputs. And how do you know it? You observe the process of addition. This is how we add. We take one bit from one of the numbers and we take another bit from the second number. So you have two inputs, A corresponding to the bit coming from the first number, B corresponding to the bit coming from the second number. And you don't see anything else here, right? There are just two inputs, true. But what happens when you add these two digits together? As we discussed in the last class, 1 and 1 will give you 1, 0, but you can only put one bit here, which is 0. So you have to give the other bit to the next position. So you provide a carry to the next position. So now if you're looking at the next position here, you have two inputs, of course, one bit coming from one of the numbers, second bit coming from the second number. So you have A and B. However, you also have to account for the carry that is coming in from the previous stage. So that means you need to keep in mind that there are three inputs. One of the inputs would be the carry in from the previous stage. The only exception was the very first set of numbers that you added. But when you design it, you could just always consider that carry in for the first stage is 0. That's it. That's how you make everything universal. So all of the adder blocks will have three inputs, A, B, and carry in. That's how we identify how many bits we are going to get. And how does that help you? When you know that you have three inputs, you can easily generate these three columns of the truth table. Because with three inputs, you have these combinations. Done. And now we have to also identify how many outputs we have. And you must have seen that when you add two numbers, you keep one bit within the same position and you provide the carry to the next position. So you need to calculate two things, sum and carry. So apparently there are two outputs, sum, which stays where the bits are, and carry is given to the next stage. All right, so we need two outputs, 1 and 2. And then, we don't have to memorize this thing at all. What we did together was try to figure out all possible combinations, and we are doing it by observing the binary addition again, right? We notice that, hey, there are three possible scenarios with the inputs that you have. You could either have both zeros with carry itself being 0. So 0, 0, 0. And obviously the sum is going to be 0 here, and carry is also 0, right? And there is just one such case, which is this one. We put sum and carry both 0. There was another situation where you could have just one. And this one could be anywhere. Notice, if this were 1, 0, 0, or 0, 1, 0, or 0, 0, 1, it doesn't really matter which one is 1. Is A1 or B1 or carry in 1? We just have to see this situation where you have 1, 1 out of the three inputs. Okay? And that means your sum is going to be 1 and carry is going to be 0 all the time. So what we do here we identify the cases like this, just 1, 1. So this is one case, this is another case, this is another such case. And notice we just put sum equals 1 and carry equals 0 for all three cases. That's how you populate it. Does that make sense? Okay, and finally, we look at what happens when you have 2 1s, what happens when you have 3 1s, and that constitutes all possibilities. Okay, and then we populate the truth table. What I'm trying to get you a feel for is that how do you come up with this truth table, right? By basically observing what happens in actual addition. And then after you populate the truth table, then you can express that in a Boolean function. You don't know the Boolean function already. I could tell you that sum is A XOR B XOR C. See, stands for carry in here. But you don't know that, right? Like the first time when you try to represent addition operation with a Boolean function, you don't really know that. So this is how you populate your truth table. So after you populate your truth table, you can then express that using the approach that we talked about. Just look at the ones. Obviously, sum is one of your output. When you represent sum, let's get to this one. When you represent sum, you should look at only the cases with one, because I'm gonna go for sum of product form. Okay, and you can easily see this is gonna be a prime, b prime, a prime, b prime, carry in, and the second one is gonna be a prime, b, carry in prime, and so on. Right? There are 4 terms. Are you all with me so far? Okay, so this is something that you can easily come up with based on the understanding that we have. Now, you can do some Boolean calculation and you can find out that apparently this is nothing but A XOR B XOR C. Okay, this could be homework, but I'm not going to say it as a homework. It's going to be too boring. But you could either do it with maths or you could do it with observation. Let's do the observation first. Notice, let's take a look at where the output becomes 1. Just take a look at it. Let me mark them with, can anybody see a pattern here? 1, 2, 3, 4. Can anybody see a pattern here? Thank you. Yes, right? You see that immediately. Let's look at all the other cases. For all the other cases, you have either 0, 1 or 2 ones. Notice that, right? That means even numbers of ones. No, the cases where you have odd numbers of ones, you have output 1. Otherwise, it's always 0. Still with me? So this symbolizes, so this basically is the concept of 3-bit XOR or exclusive OR. Whenever you have a mismatch in a way that you have odd, even is considered matching. Let me go back to here. If it were like 2 inputs, notice when both 1 appears, both inputs 1 becomes 1, then you consider that it matched. And when both input appears 0, you consider that they matched. If you have 0, 1 or 1, 0, you consider that to be mismatch. Remember that, folks? So similar to that, for a 3 input case, logically, when you have odd numbers of the same thing, we are choosing 1 as the output. And when you have even numbers of the same, like 1, you're choosing 0 as output. That's basically the essence of 3 input XOR. And also this operation 3 input XOR is often used for parity checking. Basically, how many ones you have. Is it odd or is it even? Which is also used for testing the validity of some data. Anyways, that's a tangent. The point is you could always do it with observation, but practically you could also do it with Boolean algebra. You could go back and make A XOR B XOR C. Okay, now you could do something similar for carry out. Let's see how many ones you have in the carry out section. There are 4 ones. Okay, and then you could easily represent that using the approach we know. A prime, B, C. Please help me populate this. Can anybody tell me the term for this one? Quickly. A, B prime, Ci. Right. A, B prime, Ci, or carry in. And then other 4. And then you could simplify it a little bit and you end up with this one. Okay, we are skipping those steps because we looked at it in the other lecture. So apparently this is the universal expression for sum and carry. And as you can imagine, this is heavily used everywhere. Okay, but remember, this is not the only expression. There are many other ways that people do it. And there are different kinds of adders that people use. This is most probably, I mean, not most probably, like this is literally one of the most or one of the least optimized adder operation hardware ever. There are many other better solutions that people use. Okay, now this is a block that people often use to represent with 3 inputs and 2 outputs. And the reason why we need to be mindful of this block is because after today's lecture, the very last slide of today's lecture, we'll need to use this block again for a different purpose, not for adder. And I'll show you for what. You may have already seen it, but we'll revisit this block. Uh, I didn't talk about this circuit in the last class, I remember, because I think I fast forwarded through the animation. So apparently this circuit is implementing your sum and carry. Can you see that? Can you see that? So this is a symbol of an XOR gate, and you have three input, A, B, C. So you're doing A, XOR B, XOR carry in, and that's your sum. Make sense? Yes. Mhm. You can. So basically, what you're referring to is XNOR, essentially, XNOR. So you could do the opposite of XOR. Right. Mhm. So you tested it? Okay. Okay. All right. Maybe I can take a look at the design that you have, and then we can discuss this later on. All right. Okay. So uh, where was we? Where were we? Oh yeah. So make sure, please come to my office hours, and I can sit with you and see what's going on there. All right. Okay, so by the way, typically we never use a three input XOR gate right away. We have to use it, as he mentioned, we have to use it with smaller components. And that's what you're gonna work on in your lab practically, okay? You're not gonna basically just use a three input XOR gate. You will be using AND gate and OR gate to make this three input XOR gate, okay? All right, and how about this? What is it doing? Can anybody tell me, folks? It's basically incorporating AB plus BC plus AC. Notice this is A, this is B. So you're getting AB here and BC here and CA on the other side. Here C stands for carry in, so CI. And then finally you're using this OR gate to add them up together. Are you all good? Okay, all right. So, and finally, this is the circuit that we should keep in mind. This is the last slide for the recap. So apparently you have two inputs, A and B. Let's start here. Basically, this is 0, 0. So you have two inputs of a number coming in, and you have carry input for the very first stage. Typically, this is always going to be 0, the first carry. And then it generates a sum which stays here, and it generates a carry which is given to the next stage. And then you have two other bits coming in, and it's giving to the next. This is known as ripple carry adder. Why? Because it's as if the carry is rippling through the chain. Does that make sense, folks? Rippling through the chain. That's why it's a ripple carry adder. And so finally, the final carry comes out of this. And this is the sum, essentially, that you get. Okay, so we will revisit this circuit in the last slide of today's lecture. Let's move on to the lecture now. So it's going to be a small lecture because I carved out a section from this lecture and brought it forward so that you could start working on your lab. So that's why they look really weird. Why are they so small, right? They were supposed to be one lecture combined together, but I just chose to separate them out. All right, so combinational logic, and we are continuing our discussion. I just realized that I'd never even mentioned, I mean, it's probably obvious, but still, I should mention what is a combinational logic, because there are other kinds. There is a different kind of logic, which is known as sequential logic, but we'll talk about it later. Combinational logic is a logic whose output depends only on the combination of the inputs, and it doesn't depend on the history. Okay, so imagine you have a logic block, you have a set of input A, B, C, D, and what happens to the combination? Is it 0, 0, 0, 0, or 0, 0, 1, 1, or whatever? Whatever the combination of the input is, that determines the output, and absolutely nothing else. You don't have any feedback from the output to the input. Are you all with me? There are other kinds of logic which not only considers the combination of the input, but also considers the history. What happened in the previous cycle? What is going on with the output? So there is a feedback. that also determines the overall output. Okay, so those kind of logic is not combinational. Okay, so all of the logic that we are going through right now, they're combinational logic. That's why you only see inputs and outputs. You don't see any history column showing up here. Okay. All right. This is supposed to be a quick recap, but we already have done recap with the sum, so I don't want to go through this. Let me test you in 20 seconds. Can anybody help me get the mean term and max term expression for this truth table? We did it together, by the way. For mean term, what should you look at for mean term? Just the ones. So these are the ones, okay? And which positions are these ones in? Let's see, 0, 1, 2, 3, 4, 5, 6, 7. So 3, 4, 5, 6, 7. These are the positions where you have ones at the output, all right? So my mean term expression would be the sum of all of this. And I can write it as M3 plus M4 plus M5 plus M6 plus M7. That should be my function. Simple. If you see the truth table, it's as simple as that. Or you could just represent it as the sum of 3, 4, 5, 6, 7. That's what you have here. Now, quickly, if you know this expression, can you help me formulate the max term expression now? What are the max terms? Wherever you have 0. Okay, so this is 0. So we should, whatever you don't have in this expression, just fill in those numbers, which is 0, 1, and 2. So your max term expression would be M0 times M1 times M2. So basically end of all of them, right? But we could also represent it as 0, 1, 2 this way. So you already know how to convert from mean time expression to max time expression. Let's move to the next one. What you didn't notice that we came up with this expression based on truth table. But what if you don't have the truth table? Okay, that's the other question. What if you don't have the truth table? Then what? So imagine you are given a Boolean function like this. Yes, you could either create the truth table by plugging in numbers 0, 0, 0, 1, whatever, but that's not the most efficient way. You could do it with some Boolean algebra, and I'm going to show you the strategy here. First, notice this is a function with 4 variables, A, B, C, D. There are other ways of figuring out how many variables should there be, even if this one is not mentioned. Even if this is not mentioned, just look at how many variables you have in the expression. You have A, you have B, you have C somewhere, and you have D. So apparently there should be 4 variables. Are you all with me? A and A prime, they're literals. So they're not 2 variables, by the way. They're considered as 1. Okay. All right. So there should be 4 variables. Now, this brings me to the question. With 3 variables, how many rows do you have in the truth table, folks? 3 variables, 8. With 4 variables, 16, right? 2 raised to 4, which is 16. And the cases will be like similar to this. So 0, 0, 0, 0, 0, 0, 0, 1, and so on, ending at 1, 1, 1, 1. So if you try to express them in min term and max term, they should look like A, B, C, D, A prime, B prime, C prime, D prime for 0, 0, 0, 0. And finally, A, B, C, D for 1, 1, 1, 1. Are we all clear on that? Okay, just keep that in mind. Now, I'm not going to go through that 16 rows of truth table here. What I'm trying to do is bring back the variables that are not showing up in every term, because in min term and max term expression, you have to have all the variables showing up in all the terms. If you have 4 variables, all 4 of them should show up, as I just showed you. A, B, C, D, they should be in some form, either true or complementary form, but they should be there in every term. All right. The reason why you don't see them here is because this expression was simplified. So they have given you a simplified expression already. So you don't see the mean terms in proper form. Okay. So let's bring them back. And how can I do it? Very easy approach. So notice you have A and B. What you don't have here, you don't have C and D. And remember, C plus C prime is always 1. Similarly, D plus D prime is always 1. And I can bring C and C prime, sorry, C and D in the expression by randomly adding these 2 extra terms. Are you still with me? Okay, so you had A and B already. I just decided to bring in C plus C prime and D plus D prime without changing anything. I'm just going the other direction, as you see, just making it more, expanded. Okay, how about this one? You have A and D. What you don't have? You don't have B and C. So I'm gonna forcefully incorporate B plus B prime and C plus C prime. Okay, how about the third term? There is just one thing missing. What is that? B. So I'm gonna forcefully introduce B plus B prime. That's it. That is the strategy. Super simple. Once you know it, you can do it. Okay, and then just go ahead and multiply everything. Just multiply everything. And then you're gonna end up with this large expression. Okay. Is it too difficult to do? What do you think? Hopefully it's very straightforward, okay? And you can do one or two practice at home. It should be okay. Now, one other thing to keep in mind is, notice if you expand this, you'll have repeated terms. Like for example, A prime, B prime, C prime, D appearing twice, okay? What is A plus A, folks, in terms of Boolean algebra? What is A plus A? A. So it doesn't matter how many A you have in terms of Boolean algebra. This is not addition. This is Boolean logic, right? Boolean OR. So basically, all of the same numbers with each other will always be that number. So we don't need two. We can just keep one of them. So we get rid of the redundant terms. So what you're left with here is this expression. And by the way, remember when we started discussing this, I had a table on the side and I was pointing to see what is 0, 0, 0, 0. This is what it is. And I told you that you don't have to memorize. You could just logically write down the expressions. And let's do that together here. So notice you have 4 inputs in every term. So now you're talking about min term and max terms, hopefully. You're in the right spot. Let's try to represent them with actual binary digits now. Okay. So wherever you have prime, you should write 0 corresponding to that. And wherever you have unprimed, that should be represented as 1. We are doing the opposite now. So A prime, B prime, C prime, D prime should represent what? Help me out here. 0, 0, 0, 0. Okay, let's take a random term here. Let's talk about this. A prime, B prime, C, D. A prime should be 0, B prime should be 0, C should be 1, D should be 1. Simple. Let's take another random term, maybe this one. A, B, C, D prime. For A, you have 1. For B, you have 1. For C, you have 1. For D prime, you have 0. Simple. So just fill out all of this min terms and max term expressions with this 4 bits of binary number. All with me so far? And by the way, once you have these binary numbers, you can always represent them in decimal form as well. So this 0 actually means 0 in decimal. 1 actually means 1 in decimal. How about this? 0011? What does that represent? 3. So you have 3 here. This represents 5, and so on. You can easily convert them in decimal and get the numbers. And which is, or you could look at the table if you have it somewhere, right? And oh, okay, this is just, that way you don't have to even convert this. But for the most part, it's super simple and straightforward to convert. Okay, so this is your mean term expression for the function that we chose. Okay. Now, once you have the min term expression, very quickly, can you tell me the max term expression here, folks? How many total rows should we have? 16. Starting from 0 to 15, remember that, right? 0 to 15. So you just look at the numbers that you don't have here. Max time expression would be, you have 0, 1, 2, 3, you don't have 4, so 4. 5, you don't have 6, so 6. 7, you don't have 8 and 9, so 8 and 9. 10, you don't have 11, 12, 13, you have 14, but you don't have 15. So that's your max time expression. Make sense? All right. So let's see. There you go. There you go. So you are practicing a lot because these are important, so that you can just do it on the fly without any, breaking any sweat. Still with me, folks? Yes. So first of all, min terms means you have to have all the variables showing up, first of all, in either true forms or true form meaning A, complementary form means A prime. So apparently, in any of the form, as long as you have the variables in any of the form, it should be okay. Okay. And the uniqueness about min term and max term expression is that they're exclusive, meaning they basically cover, there was a question about it. Do they cover all possible combinations? Yes, they do. So with min terms, with 3 variables, you cover all possible combinations of that variable. Okay. Similarly, with min terms with 4 variables, you cover all possible combinations of that variable, and in n format, meaning you have A, B, C, or A prime, B prime, C prime, and so on. So min terms cover all possible combinations in AND relationship, and max term cover all possible combinations in OR relationship. Does that make sense? So together, they basically complete the design space. Apparently, there is nothing else left that is possible with these variables. Okay. Does that make sense? All right. Now, so basically that's how you get min term and max term expression from a functional output. Now, another quick concept that I want to get across, quick message, is that I mean, this is a great question, which helped me point to the fact that these min term and max term expressions are complete. Meaning, for a given function, you have a min term expression, you have a max term expression, and that's it. It's unique. You don't have 2 possible min term expression for a single function. Are we all good so far? You can, okay, let's take a look at it. This is a Boolean function. If this is another Boolean function, take a look at them. Do they look similar? Do they look same when you look at the expression? Do they look same to you, first of all? This is A prime C, but you don't have A prime C anywhere. This is AC prime. You have B prime C prime. Here you have BC. So are they same in terms of like just looking at them? Are they same? They don't look the same. But when it comes to min term and a max term expression, there is just one expression. You cannot have 2 expressions for min term that are equivalent. No. This is the unique part about min term and max term expression. They're always going to be unique. The uniqueness of them is they are unique. You have one expression for a function. Okay. Unlike conventional Boolean functional expression, where you have multiple formats representing the same function, but they have different formats. They can be equivalent. But min term, max term, no equivalence, just one expression, done. That's it. So we can use this fact to check the equivalence of 2 functional expressions. For example, why is it so unique? Like, okay, we could always use Boolean algebra to convert one expression to the other and see whether they match. And we did it in the first few lectures, didn't we? Right? I showed you some examples. So this is a Boolean function, simplify it using some, approaches, and then get an equivalent expression. But take a look at this expression and try to get to the other one. Can anybody tell me what we can do to get from the left-hand side to the right-hand side? Can I take anything common here? What can I do? It's not very obvious. Both of these are optimized. You have the same number of AND gate and OR gate. Notice you need 3 AND gates and an OR gate. Here as well, you need 3 AND gates and an OR gate. Exactly the same. In terms of optimization, you don't have to further optimize. They're pretty much the same. But the expressions don't look the same. They look different. You see what I mean here, folks? How do you then go from left to right or right to left and prove that they're equivalent? How do you do it? There is another way. Remember, a function is always going to have one unique min term expression or one unique max term expression. So let's try to convert this function into its min term expression, and the other end into its min term expression. If the min term expressions match, that means they are the same function and they're equivalent. Make sense, folks? That's another way of universally checking whether 2 Boolean expressions are equivalent. So let's do it. So let's take a look at the left-hand side, which is this one. In doing so, we were also going to learn this conversion as well. So let's do it one more time together. This is important because then you have to do it on your own for homeworks or exams or quizzes, right? So makes sense to work with me in class to solidify your understanding. So first of all, in the first term, A prime C, how many variables do you have? Look at it. A, C, B. So you have three variables. Okay. So what's missing here? You have B missing. So I'm gonna bring back B by adding this term, B plus B prime. Simple. And then for the second term, you don't have A. So I'm gonna bring it back by adding this redundant term. Finally, AB doesn't have C, so I'm gonna add this. And then I'm gonna multiply it thoroughly. And after you multiply, you basically represent these numbers with what we know. No. Can anybody help me convert this to binary? A prime should represent what? 0. B should represent 1. C should represent 1. So you know 1, 1 is basically 3. So this is M3. How about this one? A prime represents 0, B prime 0, C should be 1. So this is going to be 1. Basically, when I multiply, I don't know which term is going to appear where, right? So you can always rearrange it later on in like incremental, like increasing order. Okay, so this one, A should represent 1, B prime should represent 0, C prime should represent 0. So 1, 0, 0. So that's 4. Are you all with me so far? Okay, so you basically do all that and you end up with an expression that looks like this. And you could always organize it in this form. Mean term of, you have 0, 1, 3, 4, 6, 7. 0, 1, 3, 4, 6, 7. That's what you have. All right. Okay, and for the other expression on the right hand side, you do the exact same thing like what we did in the left hand side, and then you express that into mean term format, and you'll see your mean term expression will be the same as what you have in the left hand side. So that means despite the functions not appearing to be the same, and we not getting any way from to basically just deduce right hand side from left hand side in an easy way. I mean, we could always bring in some redundant term, blah, 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 but it's not the easiest thing to do. But you can easily represent that in mean term format and check equivalence. Does that make sense to all of you? Okay, let's move over to the next one. This should be fairly easy. I already covered it actually. Okay, but we could just practice it in like 30 seconds. What this chart shows you is how to convert from one format to the other. And also, in addition to that, if you know a function, how to get the complement of that function quite easily using min term and max term format. So don't look at the chart. Listen to me and try to work with me, and hopefully it will be like super easy for us and clear to us. So imagine we are given a function. This is the function that we are given. 3, 4, 5, 6, 7. And we are told that there are like 3 variables. So we have up to 8. Okay, not more than that. Simple. And if you could do it for 8, you could do it for 16. It's all the same. You just have to write more numbers. That's all. Okay. Now, first question. If this is your min term expression, you have already done it. What is the max term expression? Simple. Just bring the numbers that are missing in the min term expression. Super simple. Did you do it together? Okay. This is taken from textbook, by the way. So I'm covering the textbook. So we know how to get from min term to max term for the same function. Okay. Now, so this is min term, this is max term. What the textbook is showing you, what if I give you the max term? Can you come up with the min term? Of course, yes. So in the min term, you have 0, 1, 2. So just fill in the rest, you get the max term, min term expression. So vice versa. You could either get min term or max term and get the other one. Super simple. But what is also interesting is you can easily invert a function or get its complement looking at its min term expression. Take a look at it. This is min term expression for function f. Can anybody guess what's going to be the expression for f prime, which is the opposite of a? Remember, an invert of a function is wherever you have 1, you're going to have 0. And wherever you have had 0, you'll be having 1. So whatever term was missing in the original min term expression will be available in the complementary function. So if you have 3, 4, 5, 6, 7, for its prime, you'll have 0, 1, 2. As simple as that. Are you still with me, folks? Okay, I'm gonna. I will help you understand the necessity and usefulness of this approach by doing this. Okay, if I ask you, if I give you a function AB plus BC plus CA, and ask you to take the complement of it, and if you try to do it with functional Boolean expression, it's gonna be really difficult for you to do. There will be multiple steps. Are you getting it? So how do you arrive at the expression with just algebra? Or if there are like 4 inputs, 4 variables, like for example, where we had here. Okay, so if I ask you to get the prime for this one, mathematically using Boolean algebra, it's going to be very difficult for you to do and very cumbersome process. But if you use this min-term maximum expression, if you know the min-term for one, you could just easily get the other one. Okay, are you all with me so far? Okay, all right. And don't get confused with this thing, which I want to also explain. Give me 1 second. It's not letting me erase this. Okay. So what I'm trying to tell you is for the inverse of a function, you don't just get the missing numbers, you also express them in min-term format. So for a function in this format, 3, 4, 5, 6, 7, its inverse will also be, make sure you express that in min-term format, 0, 1, 2. And the difference between this and the max term expression of the function, don't forget, the max term expression has product, not sum. Min term expression has sum. Okay. So some people mix it up with the max term expression. In the max term expression, you also look for the missing terms. But remember, that is for the same function. It's not for the prime. It's for the same function. And it is in the product form, not sum form. Are you all good? You guys look confused or unhappy for some reason. Okay. Yes. Yes. Oh, sorry. Give me 1 second. Yeah. Yeah. Give me 1 second. Give me 1 second. So, excuse me. Yes, the max term will be exactly the same thing. So whatever is missing in the main function will be available in the invert function. Thank you for pointing out. So let's move to the next one. This is basically the last concept of today's lecture. So I'm not really that stressed out about finishing up the lecture today. I hope, right? Am I out of time? No. Yes, we have time. So we can easily finish it. And this is a very important concept that I want to finish. And this concept is about, funny, don't care. Something that you don't care about, but we do care about the don't care here. Okay. So what is don't care expression? Let me explain that. You don't have to read it now in the class. Read it at home. I just kept it for your own sake, for you to have an easier reading. Look at this circuit, Boolean circuit. So you are driving a Boolean logic gate. It's not in a certain shape because it's not an AND gate or OR gate. It could be a more complicated gate. Okay. So it has multiple inputs and some output. And the outputs of one gate is driving the second gate. Okay. All right. Now, imagine this circuit, this logic gate N1 is designed in a way that certain output combinations will never appear. And for the sake of example, this is taken from the textbook again. I try to stay with the textbook example so that you could easily refer back to the book and don't feel lost, right? I could use a different example, but I try to stay consistent. So they randomly chose this example, 0, 0, 1 and 1, 1, 0 for some reason. So imagine we never have this 0, 0, 1 or 1, 1, 0 coming up in this input terminal. Okay. Does that make sense? How? We'll see that later. But there are ways to design circuits that will never lead to a certain combinations. So for the second logic gate, notice how many inputs are there for the N2 gate? 3. So when I make a truth table, how many rows will be there? 8. By now we know this already, right? So, and we already know this 8 combinations. Okay, so if I give you the truth table that for certain combinations, output should be 1, for certain combinations, output should be 0, notice there are 2 rows where you don't mention 0 or 1. You just mention cross. You see that, folks? Why? Because these two combinations will never appear here. That's how it is designed. Are you all with me? So that means since it will never appear, it doesn't matter what you choose to be its output. You could say that, hey, for these combinations, my output will be 1. Because you'll never have that output ever. You don't care to represent this. Or you could mention that, hey, for these inputs, my output will be 0. You just take something, you choose something randomly. That means you don't care which one you choose. Because again, I repeat that, this will never appear. Okay, that's how it is designed. So these conditions are called don't care condition. Now, which one should you choose for this condition? Should you choose 0? Should you choose 1? Or should you choose 0 for one, 1 for the other? Which one should you choose? Right? That's a design decision that I'm going to show you in the next slide. But are you getting it? So this is a conventional truth table. The only exception here is there are two combinations that will never appear. So you don't really care about them. You could either choose the output to be 1 or 0. So you are mentioning that as a don't care condition. And we're going to choose the next slide. The next slide, let's try to figure out what happens when you choose both of these to be, say, 0 and 0. Are you still with me, folks? Okay, if you choose both of them to be 0 and try to find a functional expression, I should just look for the ones, 1, 1, 1. Can anybody quickly tell me what the expression should be like? A prime, B prime, C prime. Okay, A prime, B prime, C prime. Let's do it. A prime, B prime, C prime. And then for this one, you have A prime, B, C. So A prime, B, C. For the other one, you have A, B, C. Simple. Okay, and you do some simplification, and you get this. All right. You can easily simplify stuff, as you know, right, folks? Okay. All right. So this is the expression you're gonna end up with. Now, if you choose one of them to be 1, maybe this one is 1, the other one is 0. Now you're gonna have an extra term, 1, 2, 3, 4. So you will start with 4 terms. And then you could do some Boolean algebra and simplify it down to this one. Notice, is the second expression simpler than the first one or no? Why do you think so? Because, okay, so to represent that, you need an AND gate, 3-input AND gate, yes. And for this one, you need another AND gate, but 2-input AND gate. And to represent this, you need an OR gate, okay? And for this one, you need a 2-input AND gate. For BC, you also need a 2-input AND gate. And to combine them, you need another OR gate. But notice, instead of 3-input AND gate, you have a 2-input AND gate, which is honestly significantly smaller in area. Okay. And you don't know this now, but when you take 433, you learn to design the physical hardware and physical design. And then you'll see, oh, wow, getting rid of one input is not just one input. It's a big deal. Okay. It's a big deal. So see, which one is simpler? Simply because you made a choice to pick one of them as 1 and the other one as 0. You simplified it. And you could try the other combination. What if I choose both of them to be 1? And now you have a more complicated version. You have, are you still with me? So don't give up, okay? So yes, yeah, of course it might. That's the whole point. So you are actually traversing the trajectory, like the design space, to see which one makes it easier. If I pick this one to be 0, the other one to be 1, blah blah blah. How does it change? So you see that practically that things change when you pick one as 1 and the other one as 0 and vice versa. Now, how many times can you do it? This is a simpler system where you have like 2 don't care condition. What if I had 4 don't cares? Imagine, what if these were also don't cares? Then you have 4 combinations, 0, 0, 0, 0, 16 possibilities. Am I gonna try all 16? No, I care about my time, right? So obviously, there is a better way to explore this. And we will learn the better way. That's practically the last slide we'll talk about. And that's the next lecture, okay? K-map approach. So that's a different, yes. Yes, exactly. So if you can, first of all, there has to be a way to identify don't care condition. If somebody tells you that I don't care about this, great. But life is not that simple, honestly. Oftentimes we have to identify don't care condition using other means. But at this stage, since this is introduction to like digital logic, we are basically being handed over things that I'm giving you the conditions that are don't care. And now take it and design your circuit appropriately or optimize your logic appropriately. But at some point, obviously, we'll learn how to identify and choose don't cares. Okay. Now, by the way, before we move to the next one, when I express this in min term and max term expression, folks, work with me on this. Just look at the ones. When I try to express this as min term expression, can anybody help me write the min term expression for this one? Summation m, which stands for min term. What should be the numbers that I take in? 0, 1, 2, 3, 0, 3, and 7. Thank you. 0, 3, and 7. And then I have to mention the don't cares. This is number 2, this is number 1, and this is number 6. Do you agree? So I have to write plus summation of don't cares 1 and 6. Okay, that's how we express this. Do you see that? Okay, so the regular terms and then the don't cares. All right. Okay. And the max term expression is exactly the same. I don't have to repeat it. Max term for the regular one, and then you separate out the max term for the don't cares. Okay. That's how you express it. Get used to it. Okay. Now, let me show you one thing here. I think I somehow copied the same slide twice, but it's fine. This is the last slide. Okay, this is the last slide for this lecture. So we are perfectly on time. I'm gonna show you. I told you that we are gonna bring back the adder circuit here, right? This is your adder circuit, full adder. You have bits coming in, sorry, this is taken from a different textbook. So it has a different way of showing things. It starts from right, goes to the left. I like it better actually, because that's how we add, right? Don't you? We add from the right to the left. Okay, so you have 2 bits coming in, 1 bit going out as carry, and the sum getting out as output. And this is the carry in. Now, this is basically not implementing an adder. It is implementing a subtractor. Can anybody tell me why? And I just think of this slide that I showed you in one of the lectures, that how do you subtract 2 binary numbers? You take the first one, and whatever you're trying to subtract from it, what do you do for that? You take 2's complement, right? And add it to the number instead of we don't have to subtract. We just have to add, right? We can use the adder block to subtract things. And how do you take 2's complement of a number? First, yes. So say, imagine you have 0, something, a binary number. You first flip it. So you just invert the number. If this is a number n, you just invert the number and then add 1 to it. That's how you get 2's complement, right? Folks, are you all with me? Okay, yes. So let me just quickly finish this first. So imagine your digits are 1, 1, 0, 1. So this is 1, 1, 0, 1. This is coming in. First, to take 1's complement, you have to invert it. See, you are using a inverter to invert it. So all these points will have 1's complement. But then you have to add 1 to it, right? Are you all with me so far? How do you add 1 to a number? Remember, the carry for the first bit adder is always 0. Remember that? Because you don't have any carry. It's just the first one. It doesn't have any carry. It will generate a carry that will move to the next one. But for the first add, there is no carry. But notice this. For a subtractor, we forcefully add a carry. Why? Because this is essentially going to be added to the 1's complement to make it 2's complement. Are you all with me? So the difference between an adder circuit and a subtractor circuit is that the first carry will always be 1. So if I give you 2 circuits, you see the first carry as 1, you say, oh, this is a subtractor circuit. But if the first carry is 0, this is essentially an adder circuit. Question? It can. Yes, you're heading in the right direction. Yes, there are many other interesting things that people do. And I haven't talked about the sign bit, and unsigned bit operation, right? Depending on that design choice and architecture choice, you could also change and update the hardware. Okay. All right, so we'll stop here because we are out of time, and I'm happy to answer questions. I'm happy to stay here. If you have questions, please come and talk to me. Thank you.